Hello everyone, my name is Ali Ayub, and today I'll be presenting a paper, a personalized household assisted robot that learns and creates new breakfast options through human-robot interaction. So with the aging world population, it is imperative to develop assistive robots that could help older adults in their homes. However, one of the challenges for these assistive robots is that they must be personalized to their specific users' needs and preferences. Further, it might become boring for the user if the robot performs the same task again and again, and it might be another important aspect for these assistive robots to be creative and perform these tasks in creative ways to avoid being boring for the user. So prior research developed semantic knowledge graphs for household assisted robots to perform tasks in the household. However, most of these works used fixed knowledge architectures that could perform assistive tasks in a household, but in a very specific way using the fixed knowledge in the graphs. So therefore, they're not personalized to their specific users' needs and preferences and the environments that they're operating in. So in this paper, we developed a novel cognitive architecture for a mobile manipulator robot to learn and create breakfast options through human-robot interaction. So we developed a graphical user interface to allow users to interact with the robot and teach different breakfast options. So for this, users can place breakfast option in front of their table and then type the name of the option in the GUI. And the users can also use the GUI to ask the robot to set up a table for breakfast. So we use a YOLO object detector trained on 20 common household objects to detect objects in the RGB camera view of the robot. And then we also combine it with the depth data for localization. And then we encode a breakfast option in terms of the objects that are present within the particular breakfast option in terms of feature vectors we call as latent variables. So once the data has been encoded into latent variables, they are stored into the episodic memory. So the users, when they teach new breakfast options, they are stored in this memory, and this is the long term. We also have a short-term memory to store the daily breakfast options that are being set up by the robot, and that way the robot can remember what the user has been eating for breakfast for multiple different days. We also developed a creativity module to allow the robot to generate new breakfast options that were never learned from the user. So for this, we use the data stored in the episodic memory to initialize a Gaussian process, which is then sampled to generate pseudo-latent variables that could possibly be different options that were never learned by the robot. Notice that these pseudo-latent variables could still be invalid options. So for example, there could be an option like cereal, milk, and spoon with a bowl missing to pour the cereal and milk. So to deal with invalid pseudo-latent variables, we learn a logic-based knowledge graph from the data stored in the episodic memory. And this graph essentially is a probabilistic dependency of food and utensil items with each other. So for example, if these were the breakfast options stored in episodic memory, we could learn this knowledge graph and realize that milk requires cup. And then when an invalid breakfast option is generated, we could fix it by adding cup into this breakfast option. And then finally, to set up the breakfast options physically, we decode the latent variables, get the object categories, and then plan lower level actions for arm and base for the robot to go and pick those items from the kitchen and bring them to the dining table. To test our system, we perform experiments on a fetch mobile manipulator robot in an indoor lab environment with 2 contexts, kitchen and a dining area, with 9 object categories placed in the kitchen area. We teach 7 breakfast options to the robot in the beginning using the GUI, and users for these experiments were the experimenters. So in our first experiment, we tested the ability of the robot to learn breakfast options from the user and then set them up on the table. We noticed that in the 7 breakfast options taught to the robot, there was no learning error. And then to test the robot for setting up breakfast, we performed 15 runs. And then in this case, we noticed that there were 10 out of 15 times when the robot was able to correctly set up a breakfast. And in the other ones, there were errors picking up some objects. And the main sources of error for our system were first the manipulation error, where the arm motion planner either failed to plan a path to the goal, which was the object, or the perceptual system failed to detect or localize an object. There were also grasping errors where the robot gripper was just unable to grasp an object even when it reached to pick the object. We then performed an experiment to test the ability of the robot to set up new breakfast options. So for this, we asked the robot to set up 5 new breakfast options, and we realized that all of them were valid options. However, 2 of those 5 options were fixed by using the logic-based knowledge graph because the pseudo-latent variables were invalid before. And again, the main sources of errors were the manipulation and the perceptual errors. So to test our creativity module on a larger scale, we tested in simulation with 25 objects and with 20 breakfast options initially taught, and then asked the system to generate 200 breakfast options. And we noticed that there were 99 distinct valid breakfast options generated by the system after learning only 20 breakfast options. Finally, we tested the personalization capability of our system. And then for this, we taught it some unconventional breakfast setups. So for example, in this case, cereal, bowl, yogurt. So in conclusion, we developed a novel cognitive architecture that allows a mobile manipulator robot to be personalized to their users by learning and creating new breakfast option through human-robot interaction. And our extensive proof of concept evaluations on a mobile manipulator robot confirm the personalization capabilities of the system. So in the future, we will focus on fixing some manipulation errors for fetching objects. And our hope is that this system can help develop household assistive robots that could provide long-term assistance for older adults in their own homes. Thank you. And if you have any questions, please let me know.